Okay, so now we are going to go back to more fluid statics, and hopefully by the end of the class understand how balloons can fly, although you already kind of know, but in detail, in engineering terms. So here's another example. In this case, we have what's called a butterfly valve, which is simply a disc that can, flip around, rotate around an axis. We're looking here a cross section of this. It has 10 feet in diameter. We'll look. It's rather large. We're using British units for this exercise. And it's used to control the flow of some outlet pipe. This is a round pipe, of course. And the valve is closed in the position that's shown in the picture, and it's supported by a horizontal shaft which passes through the center, through the axis there in the center. So find the torque that needs to be applied to hold the valve in its closed position. Okay? It's a very classic engineering problem for our statics equations, our equations of fluid statics. We're giving the depth at which the centroid of that valve is located, and the pipe is at just atmospheric pressure. So our solution to this is to use our hydrostatic pressure, hydrostatic force, and we can use the shortcut number 1, which is to calculate the force by multiplying the pressure at the centroid times the area. The pressure at the centroid is gamma h at the centroid. So this is gamma h at the centroid times area. The only nasty stuff about this example is that we're not using the metric system. And so we have to go and find the value of gamma in British gravitational units, which, unlike the one in metric system, we don't have memorized. We look it up. And so the depth is indicated here is 30 feet, and gamma is from, I've taken it from some book, 62.4 pounds per cubic feet times 30 feet and times the area of the disk. The area of the disk is pi d squared over 4. Pi over 4 d squared. D is given here is 10 feet. So 10 feet squared. Easy enough. We can have the resultant. So now we can plug those numbers in the calculator, and we'll soon have a check of my arithmetic to prove that the answer is 147,027 pounds of force. Just multiplying these numbers here. So that's easy enough, but we want to find the torque that is needed to be applied to hold this valve in the closed position. So we need to find the line of action of this force, and we know also how to do that. We can calculate the position of the center of pressure using our shortcut number 2. So y at the center of pressure, let's use this P minus yc equals to the area moment of inertia divided by yca. Here's our shortcut number 2 formula. And so that's going to give us the distance between the distance below the center of the centroid, where the center of pressure is located. Yes? 10 feet squared. sorry, it's kind of 10 feet squared. Yes? This is the area of a disk. So this is the side view, but it's actually a disk. So let's calculate the distance below the centroid where the line of action of the force is, using our shortcut number 2. And here we need to look up the moment of inertia of a disk, and we find that that is pi r to the 4th divided by 4. That is the moment of inertia. And the area is pi r squared, or again we could use this one, or pi r squared, either one. So it's yc times pi r squared. I use r here because so that I can cancel the r's from the top. And basically I can calculate this now. It's the pi goes away, r squared goes away, and I only have, so the radius is 5 feet squared. Divided by 4, that remains divided by 4, and yc is 30 feet. Yes, okay, so there's an angle here. There's the answer. Thank you. That's why I'm looking at my answer. I'm looking, why do I have divided by 0.866? YC would be, let me use it red in here, is this distance. YC is the distance from the surface to, so it's an inclined, is the slant distance from the surface. So that's where I have to use the angle. 30 degrees here and 30 degrees here. And what we have is vertical distance here, so we need to use the angle. Putting these numbers in the calculator, 0.1804 feet. So that's the line of action of the force. So here's the center of the area, the centroid, and the line of action of the force is somewhere here, and this distance is in the slant direction 0.1804 feet. So basically now I have everything to calculate the torque, the force and the distance. So the torque is going to be 0.1804 feet times the force I have over here, 147,027 pounds force. And this gives a torque of 26,520 feet-pound force. Quite a sizable torque. Okay, water is very heavy, basically. So there's not some sort of stopper here to keep this from opening, it's going to just pop right open. It's a big, very big torque that we have to apply to just keep it closed. You see? Yes? Ah, okay, so I'm not reading very well my own picture. The 30 degrees is right here, right? It's not here. You're correct. So the 30 degrees are measured with respect to the vertical, according to the, if I look at the sketch more carefully, and therefore this one is 60. You're correct. All right, another example. We have a pressure chamber, and there's some pressure inside here, P, and we know that at the section AA, we need exactly 20 bolts to hold the chamber together. And the question is, how many bolts are required at the section BB? And we're given the two diameters, the large and small. So again, we have a hydrostatic force, but in this case, the hydrostatic force is due to a pressure inside the tank. It's not due to any column of liquid. We have a pressure inside the tank that wants to push these pieces apart. So the force per bolt at the section AA is going to be, what's the area of that section? The area of that section is, again, pi 4th d squared. But, so the force is P times area, and the area is pi d squared over 4. And that's the total force divided by the number of bolts. It's going to give me the force per bolt. Where the diameter d is given. Now in the section BB, we have the same situation, but we don't know the number of bolts. So at BB, we have the force per bolt is the same pressure, P small d to the power, sorry, that's squared. Nobody corrected my little mistake there of multitasking. And we don't know the number of bolts, so it's 1 over n. And of course these forces have to be equal. So we can just make this equal to the one above. The pressure cancels out, and we can solve for n quite easily. For this whole thing to be equilibrium, it really only depends on the ratio between the diameters. The pressure cancels out. So now we can put, what is this? 40 over 20, that's 1/2. 1 over 4th, 20 divided by 4 is 5. So just 5 bolts are needed in that area. Yes?
So the information about the bolt diameter
It's not, yeah, it's not of any use. We just know that the bolts are the same bolts everywhere, and we just, we can find the number of bolts by the ratio of the diameters. Yes? So you know what we're using here? We're using the concept of the shortcut number 3, basically, which is that the pressure here is in this curved surface, that we have pressure operating everywhere, right? Everywhere. But the total pressure is actually on that projected surface. The total pressure in that direction is the is basically the same as the pressure on the cross section here, and the same for the any curved surface. We just look at the projected area perpendicular to the resultant here. Perpendicular to we're calculating a pressure here equivalent to the pressure that is pulling these two halves apart, right? It's in the vertical direction. So we want the component in the vertical direction, and that's going to be, we can look at the projected surface in that direction. That's right. Or the projected surface in that direction as well is the same, it's also this surface. It's the projected surface at that location. So it was much easier than it would seem in the beginning from reading the problem, really. You just apply the concept. You look at here, we're looking at forces in that direction and, caused by the pressure on a curved surface. We just need to use the projected area. And again, like you said, the pressure is assumed constant throughout this tank. It's a pressurized tank of gas. Yeah, clear? Oh. Okay, so now we move to buoyancy and the hot air balloons. And this is, of course, something from physics that you may have seen before. Let's just make sure everybody's on the same page. Of course, all submerged objects experience a buoyant force. You have experienced this yourself in the beach, in the swimming pool. And this is flotation force that we know from physics that is equal in magnitude to the weight of the displaced fluid. So, just quickly, let's check that for, now that we know the hydrostatic force, we can check this, say, for just a cube to make things easy. So let's consider just a cube. Suppose this cube has all sides equal to S. And the cube is at a certain depth, submerged from a surface of liquid at a certain depth h. Okay? So we can see immediately that the forces on all four vertical sides cancel. And we're only worried about the forces on the top and the bottom face. So we have a downwards force on the top face which is, let's call it F top, equal to gamma h s squared. H is the depth of that top face. Then we have also an upward force on the bottom due to pressure. And that's gamma, and now the depth of that face is h plus s. And again, the surface area is s squared. So we can find the net upward force quite easily. Is simply the force at the bottom minus the force at the top. So gamma times h plus s, s squared, minus gamma h s squared, or simply gamma s cubed, which is the weight of the fluid displaced, the volume of the cube multiplied by gamma. So we can see that quite easily what we were expecting applies for a cube, just using our hydrostatic equation. What if we have just a regular strange shape? Like a rock or something. Well, let's consider for this rock a little column, a little piece of it, which has sort of this rectangular shape, a little small, little narrow vertical element here, and we can again see for this little small element of fluid, volumetric element, that the forces on all four vertical sides are going to cancel out, and the total force is only going to be the top and the bottom ones. And again, we can use the same argument that we've just used for the cube to see that the net upward force for this little, let's call this one, say, there's a delta z in the z direction, and these distances are dx and dy, and so we have a net for that little column of, so let's call it d, net, force net is gamma delta z times dx dy. And we can see that now we can add up all the contributions of little columns like that to complete the whole body. So we would have, naturally, by adding all of those forces, we'd have the total volume in the end. So adding up all the contributions, of all these columnar elements, we can get the total force is equal to, again, gamma times the total volume of this object. So we know how to calculate the buoyancy force for any shape. So now we can finally, a little video of balloons. This is the hot air balloon rally. At high speed. And a flying cow. Okay, so of course you know this is the oldest form of manned flight. So buoyancy force was used for flight in the late 18th century, and it works by, let me go back, it works by, no, I didn't want to do that. I'll just use that. So it works by, of course, heating up a volume of air. By heating up the volume of air, you reduce the density, and so all the air captured in this envelope, it will have a buoyancy force by reason of displacing a volume of air, right, that has a greater density because it's colder. So this picture here shows actually a temperature distribution inside a balloon. You can see that temperature is not really uniform. There's a distribution of temperature, but we can sort of use an average density and try to calculate how much force is generated by this. And let me just give you an example. I'll use this slide, which is clean, before I go to stability, to just I didn't leave enough space to give you some numbers of how this works for the hot air balloon. Of course, you know that the density of air is about 1 kilogram per cubic meter, but depends on the temperature. So what happens for a typical balloon? The typical balloon has a volume of about 3,000 cubic meters. That's typical. And there's heated air inside the balloon, which makes it buoyant. So unfortunately, I didn't find for these exact values. I found some actual values of some balloons that's going to be more useful to calculate the lift generated by the buoyancy force, in this case, of a balloon that in particular has 100,000 cubic feet of volume, which is not exactly 3,000, but it's very close, 2,830 cubic meters of dry air. So let's consider the force that is generated by this volume of air, dry air, which is heated at various temperatures. So consider temperature of, say, the standard air temperature, 68 degrees Fahrenheit or 20 degrees Celsius. Of course, that is going to be the ambient temperature, so the buoyancy force is 0 at this temperature, but let's get the density. At this it is 1.2041 kilograms meter cubic meter. And then if you heat it at 210 Fahrenheit or 99 degrees Celsius, the density is 0.9486. And if we go even higher to 250, of course the limit to this temperature is just how resistant the material is, the material of the envelope, and they use some resistant nylon that is actually able to resist over 100 degrees Celsius, but the pilots choose to operate it normally at a lower temperature so that it would last, the material will last longer, but it's quite easily capable of withstanding temperatures of 120 Celsius. So at that temperature, we would have a density of 0.8978 kilograms per cubic meter. And if we calculate the buoyant force at these temperatures, we find, well, of course it's 0 here because this kilograms force is 0 because this is considered ambient temperature. At 99 degrees Celsius, it is actually 723.5 kilograms, and at 120, 867.3. In fact, at 99 degrees Celsius, that is enough to lift an entire system consisting of the basket. Usually we have 2 burners. We have propane tanks. The envelope itself, the nylon, is quite heavy. It could be up to 100 kilograms. The envelope of the balloon itself, and up to 5 people. Again, the temperature inside the balloon is not constant. There's a gradient, like I showed you in the previous infrared image, but we can use an average temperature to calculate the forces. So now let's explain stability in the context of submerged objects. Of course, you know the concept of stability from your basic physics, and you know that something is stable when, you know, the typical idea of having a marble in the bottom of, say, a valley, and you know that this is going to be stable because if I displace the marble a small distance, it will move back to the previous position. That's the concept of stability that we know. Of course, if we put the same marble at the top of a hill and it's perfectly stable here, by moving it just a small distance, it will move away from the previous position. And so we understand this situation to be stable and this situation to be unstable. The same concept applies. If we move something from the position of stability a small amount and it goes back to the previous position, the situation is stable. If we move something from the position of stability a little bit and it goes away from its previous position, then it is in an unstable situation. So that is the same concept that we use for submerged bodies. In the case of submerged bodies, the situation is the following. We have the possibility of a rotation from equilibrium, from any position of equilibrium. So if this is equilibrium and we rotate a little bit the object, we want to see whether the torque that is generated restores the object to its previous position or moves it away. So in this case, we take this sort of egg-shaped object that is heavier at the bottom, so that the center of gravity falls below the center of buoyancy. The center of buoyancy is the point of action of the buoyancy force, which is located at the volumetric center. So if we move this a little bit, rotate in this way, and we look at the torque that is generated by this new position, we see that the weight acting down from the center of gravity and the buoyancy force acting on the center of buoyancy both act together to produce a restoring couple, a torque force that restores the body to its previous position. This is the stable situation, and it always happens when the center of gravity is below the center of buoyancy. On the other hand, if the center of gravity is above the center of buoyancy, what we have when we take this little egg-shaped object, which is heavier at the top, and just displace it, rotate it a small amount, you will see that the weight acting here and the buoyancy force acting through the center of buoyancy produce a couple that tends to move the whole shape away from its previous position, tends to overturn this shape from its previous position, and this is an unstable situation. And this happens whenever the center of gravity is above the center of buoyancy. Does it make sense in terms of your sort of basic idea of stability? Now this is for an object that is completely submerged, but things can get a little more complicated for things like ships that are partially submerged, because then for an object that's floating, what we have is that basically, as the body rotates, the location of the center of gravity, the center of buoyancy may change, because the center of buoyancy is related to the center of volume of the displaced volume. But if we rotate, this ship object, the displaced fluid, this volume changes, and so the center of buoyancy moves a little bit. So it's a little bit more complication. And in these situations, it may happen that the object is stable even though the center of gravity is above the center of buoyancy. So it's more complicated in this case for flotating bodies. The location of the center of buoyancy changes as the ship or any flotating object rotates. So we could have a restoring couple in this situation where we rotate this ship a little bit, and the buoyant force shifts from C in this picture to C prime in this picture, because you see now the volume has moved a little bit and there's more volume on the right than on the left. And because of that shift of the point of action of the buoyant force, then we could get a new centroid of the displaced volume such that there is a restoring couple. So the determination of the stability of flotating bodies is really complicated. It's much more complicated than that sort of usual idea that you normally, the usual sort of rule that you're told is that if the center of gravity is below the center of buoyancy, the thing will be stable. If the center of gravity is above, the thing will be unstable. That only applies for completely submerged bodies, so it's okay if you're a submarine, but for everything else, it's much more complicated. And this can be very difficult, and it's quite an elaborate engineering activity to actually look at the stability of cargo ships and so on. So we have a last subject in the chapter of stability, which is to look at the situation where at the subject of statics. So this whole section of the lectures has been about fluids that are static. But in fact, the same analysis can be used for situations where the fluid is accelerating, but in uniform acceleration like a rigid body. Because when it's moving like a rigid body, in the sense that every little element of fluid is moving at the same exact acceleration, then there's no relative motion inside the fluid. And if there's no relative motion inside the fluid, there's no viscous forces. And if there are no viscous forces, then we're again in the same situation that we were for this whole section of statics, where the only forces involved are pressure and weight. So that's the situation here. So the equation looks pretty much the same. So remember the equation that we had from the beginning of this section. We looked at a situation. We saw that the gradient of pressure. So we saw before we had the gradient of pressure in the x direction equals 0, the gradient of pressure in the y direction equals 0, and the gradient of pressure in the z direction equals minus gamma. Remember? From the beginning of the lecture. And now what we do is write this as a vector equation. Using, as you recall, the gradient, the divergence operator, which is equal to d dx, d dy, d dz. And using that operator, we can write these three equations together as one by doing, in the case of statics, we could write that the gradient of pressure equals minus gamma. This is what we've seen until now. But we only are worried about the vertical direction. We don't have to worry in general about the x direction and the y direction. So now what we're saying is we're going to have in addition an acceleration, which we don't know which direction applies, so we're going to keep this vector equation. Sorry, has to be some sort of vector in the k direction. Say the k, this would be your unit vector in z direction for your usual z, x, y coordinate system. So now we go back to this vector equation, but we have an additional acceleration, and then this is where this equation comes in, which is the same as the static equation, but instead of equals 0, it equals mass times acceleration. That's all. So now we can look at, so again, note that there are no shearing stresses. It's the same as statics in that sense, only pressure and weight are involved, but there's some sort of uniform acceleration. For example, consider some linear motion. If we have linear motion, we could have, say, your typical cup of coffee when you're driving a car and you suddenly brake. The whole coffee moves in a certain direction, right? So what happens here, cup of coffee experiences an acceleration and the surface becomes inclined by this acceleration. So we have some sort of we have acceleration in the z direction and in the y direction. So a y, a z, and the total vector of acceleration is there. And in this situation, some acceleration, the braking action in your car, or in the T, you're holding a cup, the braking action is like uniform acceleration in a certain direction. So this is what we're considering. We're considering AX equal to 0, and so dP dx equal to 0. And AY is different than 0, is some sort of accelerations, and so we have, this is a given acceleration, so we have dP dy equal to minus rho and the acceleration in the direction of y. And similarly dP dz, but we have in addition in the z direction we have gravity. And so here we have minus rho times gravity in the z direction plus the acceleration. So you can see that if we look at a small variation of pressure around a point, consider a point yz, some point in here yz, okay, in this sort of cross section. And I look at a small variation of pressure. It's going to be dP equal to, using my sort of Taylor rule for a function of two variables, dP dy times dy plus dP dz times dz. So I know dP dy and I know dP dz from above. I'm going to change colors to make it easier. And so I get dP is equal to minus rho ay, that's in the y direction, dy minus rho gaz dz. So now we can look at the line of constant pressure, and a line of constant pressure is dP equal to 0. Where do I do that? Let me see. I have to clear up a little space. So let me clear up this, we have already written that out, so let me just clear the space. to continue here without erasing the whole working that I have below. So now we look at a line of constant pressure, and that is dP equal to 0. So that means that we have minus rho AY dy equal to rho G plus AZ dz, which gives me a slope, dz dy. I can just simply rearrange these things a little bit. dz dy is equal to minus AY divided by, rho cancels out, and I get just G plus AZ. So this indicates that the actual line of constant pressure is a slanted line, which has this line that I've drawn here, basically. This is the slanted line of the surface. The surface of the fluid is a constant pressure. This slanted line here has an angle, a slope, which is given by AY, G plus AZ. So this is the inclination of that surface, depends only on the acceleration. Pressure is constant along the surface, and whenever we have an acceleration component AY, which is different than 0, the surface is going to be inclined by an angle given by this result here. All lines of constant pressure will be parallel to the free surface. The final case that we will have to see next class is the case of rigid body rotation, where instead of having an inclined line, we will have a curved line involved.